Okay, so this is kind of a difficult section, but just kind of bear with me. We'll kind of get through it. Um, so the first thing I want you to do is I wrote this part down. Optimization is the process of finding the maximum or minimum value. All right, so doesn't it make sense if you want to optimize something, you want to find the maximum or find the minimum? So whenever the question says if you want to maximize something, that's what you're going to be using calculus. Okay. All right. So then the other thing I did is we can find the solution in three ways. We can use technology. We can use analytical methods, which is like finding the max. If it's just a parabola, we can use that to find the max of a parabola or the min of a parabola. Typically, we use calculus. Okay, those are the three things that, three ways we can find it. And so we look for where the first derivative is 0. I also look for where the first derivative does not exist, because that also can be a thing. And you have to use endpoints. The way I wrote this, the max and mins can occur three ways. F prime equals 0, F prime does not exist, or the endpoints. These are the three places we're going to check to find max and mins. So basically, we've been doing this. We've been finding where the derivative is 0. We've been finding the max and mins. This is just finding it within word problems. That's what sucks. All right, I didn't do this. Okay, so this was just the title for this. Basically, we're going to find a value where x equals that makes the derivative equal 0. And I wrote all of this part down. So we've been doing this. We've created our sign charts. When it goes from increasing to decreasing, that's when we have a max. When it goes from decreasing to increasing, that's where we have a minimum. I would always just say local, because you're just not always positive there. The second derivative test is actually a new one, so this is going to be important. So if we find where the first derivative equals 0, first of all, this is talking specifically when x is a, where the derivative is 0. If the first derivative is 0 and the second derivative is negative, less than 0, let's think about this. If it's negative, that means it's concave down. So if it's concave down and a 0 slope, that's why it's a max. If the second derivative is positive, concave up and a 0 slope, that's going to be a local minimum. So when you think through this, this makes sense, but you don't always think about it. So that's what we have to kind of focus on today. All right, so don't write all these words. I literally just, step 1, I wrote draw a picture. I'm going to say your picture is the most important part of this, because you have to have a clear understanding of what this is about. Number 2, you need a formula only using one variable. Getting it to one variable is sometimes the hardest part, and so that's what we're going to work on. Third step, take the derivative, do your sign diagram test, then your second derivative test if necessary. Figure out your optimal solution. That's where endpoints, the derivative equals 0 or does not exist. Now, step 6, write your answer in a sentence. A lot of times, people go through all of this work and they don't actually answer the question. So we recommend step 6 to make sure you specifically answer the question. Go back and read the question. You don't want to go through all that work and not answer the question. And you'll kind of see what I mean as we get started. Okay, so this first one isn't a terrible problem. So we've got a tin, a rectangular tin. And what we're going to do, this is 25 here by 40. And we're going to cut out squares. So let's call that X. So that we can fold the corners up and create a cake dish. All right, so you don't make the cake dish, but you know, we have companies that actually go through this to figure out, I want to create something with the maximum volume with this piece of tin. All right, so whatever you're maximizing, that's the formula that you've got to have in one variable. So what's the volume in general of a rectangular prism? Length times width times height. So what I want to do is create an equation just using X. So let's think about this. If this picture started out 40 and I cut this out, and fold it up, fold it, how long is this across now? This will be easier if we come back into class. I actually use a piece of paper and cut these corners out. It's easier to see. And if you fold this up, you're missing these two. I'm missing this part and this part. That's why this inside is 40 minus 2x. If this is 25 and I'm doing the same thing, I'm folding this side up and this side up, my width is 25 minus 2x. And how tall is it if I fold this up? This is just x. So I'm going to write an equation of the volume of my length times width times height. That x all by itself, though, I'm just going to put in the front just because I don't like it at the end. So this is the volume of my rectangular prism. And before we take the derivative, we want to simplify this. So I'm going to distribute. I'm going to wait for the x at the very end. So I got 1,000 minus 80 minus 50 plus 4x squared. I can combine like terms, and so I don't have to write it again, I'm going to distribute this x. Now, so we get 1,000 x. This is negative 130x. So when I distribute my x, that'll be x squared plus 4x to the third. So I combined this and distributed the x all at the same time. All right, so if you look back or look up top, we had to make a formula. This is our formula. The third step, take the derivative. It's kind of nice because the first one, the picture was drawn for us. So when we take the derivative, then we're going to find the max and the mins. So we need to set the derivative equal to 0. So this one's kind of mean. First of all, we can factor out a 4 because there's a GCF of 4. And this is factorable. I will say they're a lot nicer on the IB test. This is kind of mean. This is actually factorable, but it's kind of yucky because we're going to use 50 and 5. And then we're going to use 3x and x minus minus. So we get what makes this equal 0 is 50/3. What makes this equal 0 is 5. Okay, so one of the things when we're talking about a real world problem is we want to think about the domain. So, because that's going to help us with our sign chart. So if we look at this picture, if I think about x, if this is a real pie plate or whatever you want to call it, cake dish, does it make sense? My x has to be greater than 0. This is my domain. Each of these sides have to be greater than 0. So anytime you're working with a real world problem, just know you're going to start greater than 0. What does it have to be less than? So let's think about this side here. What would make, I need this to be positive also. So first of all, if I set this equal to 0, the biggest this can be is 20, and not including 20, but that would make this side 0. So I know this side has to be less than 20. What would make 25 minus 2x equal 0? So I'm just going to kind of look at each of the sides. So this side can't be greater than 12.5. So I know that my x value has to be somewhere in between 0 and 12.5, because if it's any bigger than that, it's going to make this side a negative value, which doesn't make sense if we're talking about making a dish. Okay, so if we think about this, I'm going to start at 0. I have to end at 12.5, and it's got to be, my max and min has to be in between. So I'm going to disregard this as one of my options because this would make one of these two negative. Actually, it makes both of them, I think, negative. So we're just going to consider 5. Okay. Now we have to do our sign chart, testing out, is it positive or negative? So let's pick 1, and then we always plug it back into the derivative. If I plug 1 into the derivative, this ends up being positive. If I plug 6 back into the derivative, this ends up being negative. That means my function's increasing, 0 slope, decreasing. So that's why this is a maximum. And so we have to show this because we're trying to prove that it's a maximum volume. So we use the sign chart to help show this. So x equals 5. This is our optimal solution. This is our maximum. All right. So it says what size squares must be cut out to produce the cake dish. So we would say the maximum volume is obtained when I cut out 5-inch squares out of the corners to create my cake pan. And you actually would write that. I've run out of room and to write a sentence. Okay. All right. So this one is a little bit different. I think the hardest part of this one, it starts with 4 liters. So you probably don't remember this, but back last year in the first red book that we did, we talked about capacity. I'm pretty sure they're not going to do this to you, but you can actually look back in your notes with capacity. 4 liters is the same thing as 4,000 cubic centimeters. So this is volume, this is capacity. So we're looking at, if it's 4 liters, it tells us the volume of this is 4,000 centimeters cubed. And so we're going to use that information to minimize the surface area. All right, so just kind of put that on hold for a second. This says there's a square base. So that means this side is x and this side is x. And whatever this side is, let's just call that y. So if we want to minimize the surface area, first of all, what would the surface area of this prism be? If we think of the base, that's just x times x, x squared. Now let's think of the face. This right here. This is x and this is y. Oh, this is y, sorry. So this area is x times y. This area is x times y. This side over on the left is xy, and this back side. So the surface area of all around the sides, we have 4xy. Okay, so here's the problem. When I'm minimizing my surface area, I can only use one variable. So I've got to substitute something in place of y so that it's only using x. This is where this comes in. So what's the volume of a rectangular prism is length times width times height. So in this case, x squared y. But I know this particular prism has a volume of 4,000 cubic centimeters. And so what we can do is use this equation to substitute. I'm going to solve for y. And then I can replace this y with all of this. So now I'm just using one formula, a formula with one variable. But let's simplify this down just a little bit, because this x can cancel out one of these x's. So I get 16,000 over x. All right, so this is my surface area formula in one variable for this particular problem. Then I'm going to take the derivative. So then I have 2x. Remember, let's move this up. Let's think of this as 16,000 x to the negative 1. So when I take the derivative, I bring my power down, negative 16,000 x to the negative 2. All right, so now what we're going to do is set this equal to 0 so I can maximize, or I guess minimize in this case. I want to find the minimum value. That's where your derivative equals 0. You're going to need all the space available. You know what, let's put that x back to the denominator here. All right. So now I'm just going to add this to the other side because I want to solve for x. And I need to get this x squared out of the denominator. So I'm going to multiply both sides by x squared. Then divide by 2. If 8,000 equals x to the third, I can cube root both sides, and I get x equals 20. That's next. All right, so let's think about this. This is a real world problem, so on my sign chart, I have to start at 0. And then I'm going to go to 20. Since our volumes was both in x and y, we don't really have an ending point here. So let's think about between 0 and 20. Let's just say plug in 1. If I plug 1 in up here, that's going to be negative. And if I plug in, I don't know, 30 up here, That's going to be positive. So it's decreasing, zero slope, increasing. Therefore, it is a minimum value. We have to use the sign chart to show that it's a minimum. Okay. Oh, you know the other thing no, this is all we're going to do. Okay. So then what we've got, let's go back up and look at the problem. We want to find the most economical shape that minimizes the surface area. So this is where x is 20. So x and x, these are both 20. If this is 4,000, if I want to find my y is going to be 4,000 divided by 20 times 20. 20 squared is 400, which is 10. So my shape is going to be 20 centimeters by 20 centimeters by 10 centimeters. Okay. Now, I'm going to say you're not going to be able to do all of this on your own. But your goal is to do a little bit more and a little bit more, and so we can get at least half our points with this. All right, last example. So infinitely many rectangles can be inscribed in a semicircle of diameter 20. This diameter 20 is going to be important in a minute. Well, it's always important, but we're going to use it in a couple ways. The question is, at what point, where do I put the height to make my rectangle? It can be anywhere. All right. So we know that this side and this side will be congruent, and this we'll call x. So looking at this particular, we want to find the largest rectangle. So we want to maximize the area. So first of all, what's the area of a rectangle? Is just length times width. But the goal is definitely to have everything in terms of x. All right, so in general, what would the length be of this? The length will be 2x. Then we need to find this width. This is the trickier part. So if this is x right here, this is going to be the radius of the circle. Well, if the diameter is 20, then I would know the radius is 10. And then this would be y, and that I know is always a right angle and a rectangle. So we can use our x squared plus y squared equals 10 squared using the Pythagorean theorem. Because right now my width is y, I need to get, if my width is y, I can't take 2x times y because I need everything in terms of x. That's the tricky part. So I use another equation here so that I can change my y into x. So solve for y. Y squared equals, let's just make 10 squared into 100. Subtract x squared. Take the square root. Because this is a real world problem, I don't need the plus or minus. I'm just going to use my 100 minus x squared. So in this case with y, because my width is y, and y equals the square root of 100 minus x squared, I can now do my area formula. My length is 2x times my width. I can't use y, but y equals the square root of 100 minus x squared. And this next part, we now have to take the derivative. So this is a product rule because 2x is being multiplied times the square root. So I'm going to do 2x times, what's the derivative of the square root? 1 over 2 square roots times the derivative of what's under the square root plus the square root times the derivative of 2x. So I'm going to put that 2 in the front because otherwise you might kind of lose that. So this was our product rule, taking 2x times the derivative of the square root plus the square root times the derivative of 2x. So this is kind of a hot mess. So let's cancel these 2's. And if we have x times negative 2x, that's negative 2x squared all over the square root plus all of this. So this really looks ugly, but this is actually okay. I need to figure out what makes this equal 0. It turns out to be easier than you think. So we're going to actually add this to the other side. So 2x over this equals 2 times the square root. Do you see that if I would divide both sides by 2, the 2's really just go away? Okay. Then I'm going to multiply both sides by this radical because I want to cancel this out of the denominator. But what happens if I take a radical times itself? I'm really just squaring it, right? So this side, the radical goes away. And this squaring or taking it times itself takes the radical away. And I'm just left with what's underneath the radical. Then I'm going to add my x squared to x squared to get 2x squared. Divide by 2 to get 50. Square root both sides, and my optimal solution is square root of 50. All right, so let's think about our domain now, so we can use our domain to help us with the sign chart. Real world problem always has to be greater than 0. What does x have to be less than? If this radius is 20, it has to be less than 10. So on my sign chart, I'm going to go from 0 to 10 and put the square root of 50 in between them. Then we're just going to check positive and negative. So if I plug in, say 1, all right, this is just kind of a yucky, I'm just going to tell you right now. If I plug in 1, I end up with a positive. If I plug in 9, I end up with a negative. Now, say that you're not really sure. I mean, say that you get through some of this and get some answers here, but you're like, oh gosh, I don't know what to do. We're trying to show this is the largest. This is kind of cheating a little. But largest means we need a max. So then you just you're going from increasing to decreasing. Therefore, the square root of 50 is a max. So what would the shape of the rectangle be if x is the square root of 50? So that means our length is 2x. So our length is 2 square roots of 50. What's the width? The width is right here. If we plug square root of 50 in, so square root of 50 squared is 50. 100 minus 50 is 50. So we also end up with the square root of 50 for the width. And that's going to be the shape. These are your dimensions of the largest rectangle that could be inscribed.